Our first speaker will be David Dvorkin. He's the Senior Curator of the History of Astronomy and the Space Sciences at the National Air and Space Museum. His research and collections center on the origins and development of modern astrophysics and the space sciences during the 20th century. He's curated several exhibitions, including Stars, From Stonehenge to the Space Telescope, and Explore the Universe, and created the Phoebe Waterman Haas Public Observatory. He's the author or editor of 18 books and numerous scholarly articles and popular articles. He holds a PhD in the history of astronomy from the University of Leicester and an MPhil in astronomy from Yale University. Our second speaker will be Matthew Shindell. He is the curator in the Department of Space History at the National Air and Space Museum, working with the collection of spacecraft, instruments, and other artifacts related to the exploration and study of the solar system. His work focuses on the history of the Earth and planetary sciences with an emphasis on the Cold War period. He holds an MS in biology from Arizona State University and a PhD in the history of science from the University of California, San Diego. And this year he published the book, The Life and Science of Harold C. Urey. Am I pronouncing that correctly? Yes. Harold C. Urey, with University of Chicago Press, which examines the changing landscape of American science during the 20th century through the biography of this scientist. And then our last speaker will be Jennifer Levasseur. She's the curator of space history at the National Air and Space Museum, where she is responsible for the human spaceflight cameras and astronaut personal equipment collection. She's curated the exhibition Outside the Spacecraft on spacewalking and Moving Beyond Earth on the Space Shuttle and the International Space Station. And she holds a PhD in history from George Mason University and has a forthcoming book on astronaut photography on the Mercury, Gemini, and Apollo missions to be published by Purdue University Press. So please join me in welcoming our first speaker, David Dvorkin.
Thank you. Thank you very much. Hi, everybody, and thank you for inviting us. This has really been quite a year for us, the 50th, the Apollo anniversary. Mapping the moon with telescopes, and my thing is telescopes, so you're going to see a lot of telescopes. But I want to talk a little bit about the interplay between the eye and the hand and how different kinds of depictions of the moon have been done in the past and how they interacted with photography, all facilitated by telescopes. We start with a, I think, very well-known person, Galileo, and I must say that a lot of these images will come from our Explore the Universe gallery in the Air and Space Museum, which you may know is somewhat over there someplace across the mall. Now, Galileo had he was not the first to build a telescope, but he was the first to really examine the heavens and then write books about it. And that's why we always think of Galileo as the progenitor here. But what he really was doing was using images as evidence. And that was a new way of doing science. He would look at the moon and say it's a physical object. It's not an ethereal object. Same for the sun. He would look at Jupiter and see that there are little stars going around Jupiter. And these are amazing, amazing revelations that pretty much wiped out the old Aristotelian idea that the Earth is the center of the universe and also the center of all motion. But this is also his depiction of the moon, and he followed the moon through its phases, realized it was a three-dimensional surface, and gave us some sense of its structure, but he was not a cartographer, and so he didn't carry it beyond this. Now, others who followed him in the 17th century had telescopes of pretty much the same character as Galileo's, but definitely they were getting slightly larger. It was very difficult, at that time. The chief technical limitation was producing glass that was clear enough and could be shaped into an image-forming lens without terrible distortion. And so that was a technology on the brink. But what you also see is a high variation of what, impressionistic view of what the moon looked like. And so lunar cartography did not start all at once. It took quite some time for the imagery to become not precise enough, but at least reproducible enough to say, oh yeah, that object really exists on the moon. Because what you're looking at is an impressionistic representation looking through a telescope. And if you ever wonder what it's like to look through a Galilean-type telescope from this period, come on over to the Air and Space Museum. You'll look through one, and it's really lousy. It's very, very difficult, and we like to show people just how difficult a Galilean telescope is to use. So telescopes did get bigger, and we also have a representative lens from this monster on display in the gallery. And these were made longer, mainly for greater magnification, but also if the lens focal length was long enough, it reduced what is called chromatic aberration. When the lenses are highly curved, they'll act like prisms. And so you're going to get all sorts of unwanted color in there, and you want to get rid of it. And that was a constant problem. Are you seeing an artifact of the lens or the actual object? Especially for something like the moon, which is black and white and very high contrast. But then by the late 17th century, some really serious maps of the moon were being developed by Hevelius, who had some of the largest of these telescopes of these genre. Now, moving into the 19th century, telescopes typically did not get larger because the goal of astronomy at that time was not classical, you might say, mathematical astronomers. Were all about measuring position and motion, not so much description. But there were some mavericks like William Herschel and his son John Herschel, who built bigger telescopes with larger apertures and were able to see celestial objects far closer and far clearer. Herschel built his telescopes. He wanted to build the biggest telescope he could and then assume that he could see the end of the universe. And with that, making a few other assumptions, determine the structure of the universe that he thought we were living in. But meanwhile, his son, back by the 1840s, got very interested in photography. John Herschel helped develop many types of photography, and he also applied an interesting photographic technique to take an image of the crater Copernicus. That is an amazing image for 1842, isn't it? How the heck did he do that? It's fake. Now, it's a calotype, and basically, this was not standard, but it was known that if you could draw the figure and sketch it and get familiar with it over nights and many nights of observing and see how the shadows move to get an idea of the elevations, you could make a plaster model and then photograph the model. That's what you're looking at. And this became actually a very popular way to look at the moon. And the Herschel one from 1842 there is really pretty impressive. Now, we're talking photography. I'm not going to get technical here, but as you probably know, and certainly looking at the wonderful exhibit on the different types of daguerreotypes and calotypes and the wet plate photography and the dry plate photography of the 19th century, when these different methods became available, I just learned, in fact, today from the curator who built this exhibit, one of the first applications talked about was to photograph the moon. And you probably say that in the exhibit, don't you? Oh, that was really fascinating. It became a real target to demonstrate the fidelity of the photographic process. So what we're looking at then are some of the first efforts. This is the first surviving, as I understand it now, daguerreotype of the moon. And there are people the person who took it, Draper, just wanted to photograph the moon. He didn't really do much else with it. But people since then, especially amateurs, have looked at this very carefully and found that what just looks like a bunch of awful, bubbles on this daguerreotype actually fit the patterns of some of the lunar features. Now, what did his telescope look like? This doesn't look like a telescope, but it was a very common way of doing early photography with telescopic instruments. So here you have the object, the sun or the moon. It goes to a mirror called a heliostat that is being driven to follow objects, and that mirror sends the light through a lens, and then the plate holder is all permanent. This is all fixed. The only thing that moves is that. Because what is the big problem of photographing a celestial object? It moves. It's a mess. The history of photography in astronomy is how do you compensate for that motion so that you get a nice clear picture? Well, techniques got better using equatorial mounts and larger lenses, the 15-inch lens of Harvard. The photographs got better. There's a daguerreotype and an early collotype from J.A. Whipple in the 1850s. We have then Warren de la Rue, and there's some wonderful stereo images of the moon in the exhibit, which really a lovely look at, and actually they include lenses in there so that you can actually see it in 3 dimensions. And that was very popular at the time. De la Rue's telescope was really quite different. It was a reflecting telescope using a mirror and a Newtonian style, so the light would come down here, reflect off the mirror up to a small mirror, up to an eyepiece. But he replaced the eyepiece with this camera on this bracket in order to photograph the moon. And it was a 13-inch refractor, which for the 1850s was a pretty darn big reflector in the world. So you can see these actually in the exhibit, and you can see how they were marketed. They became a very popular and very captivating bauble that you could go off to your family and friends. And it certainly popularized lunar photography. Getting better then, Lewis Rutherford in New York City was one of the first to adjust the lenses of his telescope to focus on the sensitivity of the photographic plate. Most of the telescopes are achromatic, so that requires focusing with 2 different lenses mapped together, and each one of them is adjusted to maximize the image in one particular part of the spectrum. The trouble is they don't focus in the same place. As you can see, the greens are closer than the reds. And he maximized it for the sensitivity of the photographic emulsions he was using, and as a result came out with some of the clearest images of the moon. Tracking down Rutherford turned out to be a lot of fun. He was very well off, a lovely mansion on 2nd Avenue and 11th Street in Manhattan, and the story goes that the telescope was behind there in a tent, but I have not been able to find pictures, and you think of that part of New York and there's no place to put a telescope. Where it is, everybody thought it was here, which is on Columbia University campus. That is one of Rutherford's later telescopes. He was mainly a telescope maker, sold his stuff to Columbia, but it's not the original. The telescope that survives from Rutherford's time is this marvelous beast. It's a 13-inch refractor, but it comes from just 2 or 3 years after he photographed the moon. Because when he built the bigger telescope, this 13-inch here, he switched to spectroscopy because he was fascinated with color. And that's what most historians know him for. Telescope that he did use, which he sold to Cordoba, Argentina, and it was subsequently lost, and there's no photographs of it, so I can't show you, was best depicted by this one. There's one very similar to his at Alfred University in 1863, but that's the closest I could get to showing you the kind of telescope that he used. And one of his biggest problems, beyond tuning the lenses for the photographic plate, was to be able to follow the moon, because these are rather high-powered telescopes. And the mechanisms he developed, mainly geared, weight-driven clocks, very accurate, were really quite successful. His photographs became famous. Proctor, one of the most prolific popularizers in astronomy, wrote an entire book and featured 3 lunar photographs by Rutherford. These are now very, very desirable collectibles, you might say. But now let's go back and keep moving in the century. This fellow, James Nasmyth, used this telescope, a very large reflector, and very high-powered, to look in great detail at lunar features. And he drew them. And then he made plaster casts, just like Herschel did, and he photographed the casts, and that's a photograph of a cast that you'd say, my God, that's on the moon. And he did quite a bit of this. Nasmyth and Carpenter pretty much mapped the moon in high detail. Now, why are they doing it this way? Because the eyesight was still better than the fidelity of the photographic emulsions that were available at that time. In moments of very fine seeing, when the atmosphere was stable, your eye could depict detail. And if you stayed there long enough, you could pick up enough of the detail. Whereas the photograph integrates over a certain few seconds of time and things blur out. So there was only so far you can do with photography. So I should say photography did not replace artistically, pen in hand and ink in mind type depictions of the moon. In the 1880s, Flammarion's series of lunar images were famous. They continued on well into the 20th century in textbooks. But then photography was getting better and better. By 1890, you could see, this is Copernicus, and I've been following Copernicus here since Herschel. Copernicus crater now is about 60 miles in diameter. So that gives you an idea of the size. And you're looking at it from a distance of 240,000 miles from an ocean of atmosphere. But by the 1890s, you're getting some pretty clear pictures of it. They continued to improve, but look at the telescope that took that. Also, they improved as well. That's a 36-inch refractor with a 65-foot focal length lens. It's still in use. You can visit, and they have public nights where you can be shown all sorts of marvelous things. I would recommend Saturn. It's absolutely spectacular in here. Some of the finest early photographs, though, were made by Loewy at Paris Observatory, and there's an excellent example in the exhibit. Here's an image of a drawing of his telescope. Very odd kind of thing. It's called a coup d'oeil. And those of you who know French can correct me, but my understanding, coup d'oeil means elbow. And literally, your telescope looks like an elbow like this. With the objective lens up in front, it rotates, sends the light down from one mirror to another mirror, up to a fixed focus. And this is the most important reason. Loewy was able to improve on photography because he didn't have to worry about a moving camera. The lens did all the moving. So these were really beautiful, beautiful images, but it didn't collect very much light, so it wasn't good for anything other than lunar, solar, and planetary work. So drawing, even in the 20th century, remained really quite popular. Philip Fauth continued producing very highly detailed drawings with his Mertz-Schupmann telescope, which is a special form of telescope that corrects spherical aberration, chromatic aberration in very, very creative ways. I'm not going to go into it, but his drawings of the moon in the early 20th century were considered to be absolutely the best, and he tried to actually create accurate cartography from the motion of the shadows and the timing of the shadows. He figured what the different elevations were. And can you imagine how long it took him to make that drawing? Actually, it took him about 2 months, 3 months. And here is a picture I'm proud to say. I just want to brag. This is hanging in my basement. And in 1927, I was very fortunate. I worked at various observatories when they were doing OSHA cleanings, and it was either grab what you could or let it disappear. And I wasn't the only one. I had plenty of other graduate students competing, so we have all sorts of good stuff as a result of this. Now, moving on, though, into the modern 20th century, there were tremendous advances not only in telescope design and in photographic design, but in the photographic emulsions themselves. And this is the modern era now when you're looking at Copernicus with a photograph from a 60-inch reflector at Mount Wilson in Southern California, which happens to be, it's about a mile high, and it's very, very good seeing. And if you take 50 or 60 images with this, 1 or 2 of them are really going to be sharp. And that's how they did it at the time. They didn't have plate stacking, like we do today and all of that sort of thing. But these were very high quality in the 1930s. The improvement in photographic emulsions was also spectacular during this time, moving into the red primarily, and you can see in the time range photographic between 1904 and about 1932. And by 1932, we were being able to penetrate well into the infrared and take very fine images in areas that were very stable in atmospheric conditions. And that's how they did it at Mount Wilson, working with C.E. Kenneth Mies, who was the chief of photographic development at Kodak in Rochester in the 1930s. A real revolution. And so this was a real maturing of the photographic era in astronomy. Now, at about the same time, we have planetariums. And I'm going to break from talking about photographing the moon to going to the moon, which was one of the biggest turn-ons if you go to a planetarium, starting in the late 1930s. Both the Hayden Planetarium in New York, the one in Adler in Chicago, and the Griffith Observatory is very well known. Griffith's was connected to Hollywood And you can see that, there's a way that you can, I remember when the first time I saw this projector, it looked like a giant ant. And you can well see how terrifying it could be. But at Griffith, there happened to be a selenographer, a devoted lunar astronomer who was absolutely captivated with producing very high quality lunar detail. And here he is there. And this is a plaster cast based upon the best photographs from that 60-inch of the lunar crater Copernicus. It's 8 feet in diameter. And when I still was visiting there, it was still there, and they've used it for all sorts of purposes. Now, what I'm going to do, though, is try to recreate what turned me on to astronomy, to give you a sense of it. And it has to do with the moon. There's Alter in a very creative double exposure with his Zeiss projector, and his whole goal was to get people to feel like they're going to the moon. And that will, of course, introduce the next talks. There's Alter, and he sponsored the development of all sorts of very sophisticated projectors in his time, certainly the 40s and 50s. And between 48 and about 1953, he had a series of trips to the moon that got more and more spectacular. One of the most spectacular, which is the one I'll try to depict here, is actually traveling to the moon, and out of an aperture, you would tour the moon's surface, and Alter knew it as his own home neighborhood. He knew every crater on the moon and could tell you the history and the nature of the person it's named after. And so what I want to do is just recreate for you what that feeling was like. And I remember as a kid being taken to the moon in a series of larger and larger photographs. And then when we got to the moon, Alter would talk about Copernicus, and we could move it around up to Eratosthenes, that crater, and there are the Apennine Mountains around Eratosthenes. Moving back to Copernicus, we could move to the Carpathians, and he would talk about every crater. Now, remember that guy, Philip Fauth, that I talked about, who was drawing those craters? Well, even Fauth is on here. The two little craters right there, oops, sorry about that. Fauth A and B were named in his memory. So one way to get yourself on the moon is to be a selenographer. There is an Alter also, but it's on the opposite side of the moon, since he lived too long. Now, I sat through those programs, and I was absolutely captivated. And after that, I said, I have to photograph the moon. So here was my attempt. I built a small reflecting telescope in the mid-50s and put my grandfather's Graflex camera, a 4x5 camera that he used for professional purposes, on it, sort of balancing the whole thing off. And I took a series of pictures of the moon, and that was my first exhibit at a science fair in Los Angeles. And being able to do that and then do all the developing myself and everything was really a great kind of introduction to that. I got very happy with that. And by the 60s, I was using bigger telescopes like the Lick telescope, and I was at the observatory. But what we were doing here, I was doing astrometry, which is the distances and masses of stars and stuff like that. But every so often, my boss told me that I had to help a geologist who was coming to Lick to map the moon in great detail. And I won't go through all the details, but I got fascinated with it. And here's one of his images, Harold Mazursky of Copernicus. What were they doing? They were looking for interesting places to land. So this was the introduction I had to, oh my God, we're going to the moon. I mean, just because I was interested in astronomy, didn't know I had no idea what was happening in space. But there he is, Hal Mazursky, and he turned out to be the dean of lunar cartographers. And the highest resolution images that were still being used were visual maps at that time. And again, that was because the photographs had to be taken several seconds long or maybe whatever duration, and the atmosphere would fuzz out. That was the whole reason for going into space. And so with that, let's go to the moon. And I turn it over to one of the other of you, Matt.
Okay, so you've now seen the moon through telescopes. Now we're going to look at the moon through the photography that was done by the robotic orbiters and landers that were sent to the moon prior to the Apollo program. When I talk about lunar photography and when I talk about especially planetary and lunar geology, I usually like to start by talking about Thomas Much, Tim Much. He was essentially the author of the first textbook of planetary geology, and this was it, Geology of the Moon, a Stratigraphic View. And Much was a stratigrapher. He was a professor of geology at Brown University. And in 1967, he decided that what was going on with the moon was really very interesting. It was more interesting than any questions that he had about the Earth. And so he decided that he was going to take a sabbatical and go off to the newly founded astrogeology branch of the USGS, spend some time with the geologists there. And from that experience, and also from the frustration that he felt that a lot of the images that they were using that had been taken by spacecraft weren't available to most geologists who are out in the academic community, he decided that he wanted to publish a book that would sort of capture those images and collect them together, and then also develop a method of using those images that other geologists could use. So he decided he was going to write this book, and because of his own biases as a stratigrapher, it was going to basically be a stratigraphic approach to looking at the moon. And I like to show the first pages of the book because his choice of image for the frontispiece, I think, is very telling. Ansel Adams' Autumn Moon, the High Sierra from Glacier Point. It was taken in Yosemite National Park during Adams' time there at Yosemite. I think the visual argument that Much was making here is really very literal. It is that the moon is an extension of terrestrial terrain, that it could be studied as though it's an extension of terrestrial terrain with the same methods that geologists had perfected over the years of studying the Earth and studying the history of the Earth through what was visible in its terrain. One of the notes that Much makes here is that we've basically entered a new era of spacecraft photography of the moon. He says, the sudden surge in photographic information following the success of 3 impacting spacecraft, the Rangers, 5 soft landing spacecraft, the Surveyors, 5 orbiting satellites, the Orbiters, and several manned orbiting and landed spacecraft, the Apollos, and various Russian spacecraft, the Zons and the Lunas, is truly unprecedented. Almost the entire moon has been photographed with a resolution of 100 meters or better, and overlapping photographs provide stereoscopic coverage for many areas. So basically he's saying, it's there, the data is there. We can now do the geology of the moon because we know essentially we have 99% of the moon available to us through these photographs. And so the photographs he's referring to are ones that started to come back in the late 50s as a result of the space race. So the first was October 7th, 1959. This is the first image ever of the far side of the moon that was sent back by the Soviet Union's Luna 3 spacecraft. You don't see that much detail in this photo, but still, it was enough to reveal that the far side was not quite as visually interesting, I suppose, as the near side of the moon. Then in 1964, July 31st, the first U.S. spacecraft image of the lunar surface. This was the Ranger 7 spacecraft, and you might wonder why the first U.S. image is from a Ranger with the number 7 and not the number 1, and it's because there were basically a number of failures on the way to Ranger 7 that meant that it wasn't until the 7th mission that they ended up with lunar photography. So Ranger 7 was an impacting mission. It crashed into the moon. It was actually designed to do that, and 3 times it did it correctly with 7, 8, and 9. In the case of Ranger 7, it actually returned over 4,300 images before crashing into an area that they later named Mare Cognitum, which basically means the sea that has become known, because it had now been photographed in high detail by Ranger 7. You might wonder how, within a matter of, we're talking about 17 to 20-some minutes of descent, how it was able to capture that many images at once. And if you look, there you see me with my twin, the conservator David, as we were working on cleaning our Ranger spacecraft. And when we were cleaning our Ranger, which is essentially an engineering model that was used for testing some of the systems on the Ranger spacecraft. So it never went into space, but it's been hanging at the Air and Space Museum for many years, I think pretty much since the museum opened or shortly thereafter. You can see in the image on the right, when we took off the metal skin of the spacecraft, what we saw in there were 6 Bausch & Lomb lenses, and those lenses are connected to a television camera system designed specially for this mission by RCA. And so those 6 cameras were all essentially pre-programmed to take a series of images as it was descending. So those 6 cameras were all working, nonstop, full-time on the way down to the moon. And so by the time it got to the surface, it took an incredibly high detail image of one very small part of the moon. But as you can imagine, when it first started, you're getting larger and larger swaths of the moon. Then in 1965, more images of the far side of the moon, courtesy of the Russians. This was the Zond 3 spacecraft. And this time you're able to see a little bit more detail than you were with the Zond 1. You're starting to see more craters, although it's still not quite as cratered as the near side of the moon. And then the first soft landing on the moon, the Luna 9, also a Soviet mission. You can kind of get the sense that Americans were feeling that the Russians were doing very well with the moon. and maybe we were floundering a bit at this point. But nonetheless, the world pretty much celebrated this high detail image of the moon. Even the Americans who were watching, I think, watched with a little bit of professional jealousy, at least on the part of the geologists. But then in 1966, we landed our first soft lander on the moon, and this was the Surveyor 1 spacecraft. And with Surveyor 1 and the surveyors that followed, we were able to get imagery of the moon that was essentially what you would see if you were standing on the moon looking at the horizon, because the height of the camera on the Surveyor spacecraft was basically the height of the human eye. So if you mosaicked enough of the images, the high detail, high resolution images that were captured by this camera system, you could begin to piece together very high resolution mosaics of what the lunar surface looked like and what it might look like to an Apollo astronaut if they were walking out at a particular landing site. So as you can imagine, these were sent to areas that were thought to be potentially good landing sites for Apollo. Well, one of the complaints that the geologists had about these images was that even though you get great detail from these, it's very difficult to tell distances and scales, so they're not actually geologically that valuable, except for those images that were taken when it was pointed straight at the ground, and where you could see the actual grain size of the lunar soil. And then some of the Surveyor spacecraft actually had scoop arms that were able to dig trenches and determine the mechanical properties of the soil, and they also had a chemistry experiment, essentially, that was able to tell what the composition of the lunar soil was and determined that it was a lot like the volcanic basalt that we have here on Earth. So these missions gave us our first real idea or understanding of what the moon might be like as a landing site and what we need to take into account for a spacecraft that would be landing there. But the first really systematic program to photograph the moon in its entirety was the Lunar Orbiter program that ran from 66 to 67. I have a typo there in the slide. But this was 5 orbiting spacecraft, each of which carried a dual lens camera system that was able to, I'm going to show you a photo of the camera in a minute, so you'll get a sense of it, but it was able to take photos in medium resolution and high resolution at the same time. It had a wide angle and a narrow angle lens on the camera system, and that camera system was actually designed by Eastman Kodak, and it was derived from designs that had been developed by the National Reconnaissance Office for the U-2 and the SR-71 spy planes. So this was a spy camera that had been adapted to a lunar camera. And altogether, they returned 2,180 high-resolution and 882 medium-resolution frames from the moon and mapped about 99% of the lunar surface. And I say there with a resolution of 100 meters or better. The better is pretty impressive. The highest resolution that they got was 1 meter resolution when the spacecraft were closest to the moon. So this is the Lunar Orbiter when it was being prepared, some last minute. I actually think this is probably, NASA put the caption on this image, it was an official NASA image that says this is being prepared for flight, but I don't think so. I think this is actually a engineering model that they took a picture of, because usually you don't just have a guy in sleeves rolled up making adjustments to a spacecraft. Even back then, they were a little more careful than that. But you can see how they've got the delicate gloves and hairnets on when they're treating the camera system itself. That gives you an idea of what the camera system actually looked like when it was not inside of the spacecraft bus. It's really an impressive machine. If you look at a schematic of how it actually works, all of the spacecraft I showed you before used television cameras to record images and send them back to Earth. And it's a relatively easy system to use because television signals are easy to transmit, they're easy to collect and translate back on Earth. We have that technology, right? Television is something that by then was in wide use. But spy satellite cameras, spy plane cameras used film. And the only way really to get good high-resolution images that would be useful in selecting landing sites from orbit was to continue using film in that way. So how do you have a film camera and return images to Earth? Well, they developed a method that was able to develop the negatives on the spacecraft and then run those negatives through, you see there the line scan tube, which is pointing, so this is pointing a beam of light at the negative as the negative is going through the system. And then this photo multiplier tube is collecting the light and translating it into a video signal. And then that video signal is being sent back to Earth. It's being recorded on magnetic tape back on Earth, and it's also being transferred to 35 millimeter film back on Earth. So it's a very complicated sort of Rube Goldberg apparatus of how to take a photo on film and then get that image processed and developed and sent back to Earth without ever having to collect the film, which is what you would have had to do with a spy satellite or spy plane, where the film canisters, in the case of the satellites, were dropped and then collected. But when you're on the moon, there's no one to collect it, at least not yet, right? So Lunar Orbiter, the first Lunar Orbiter, was partially successful. The wide-angle camera worked very well. The narrow-angle high-res camera was smudged somehow. So it was a little bit of a disappointment, and it never quite made the front page, the successes of the first Lunar Orbiter. It was always, below the fold or in the internal section of the newspaper, even though it did get written up in the New York Times. But it also, though, produced some pretty incredible imagery. This, for example, is the first good image of the Earth photographed from the vicinity of the moon. And this was a Lunar Orbiter 1 image. So we like to think about the Apollo 8 image of Earthrise as being the first image of the Earth from the moon. And it is the first image that a human took of Earth from the moon, but a robot got there first and returned this image. So when Lunar Orbiter 2 actually did work completely, both the high-res and the medium-res camera, it was front-page news. So for the Boston Globe, this is actually a picture. David showed you multiple pictures of Copernicus crater. This is Copernicus crater from an oblique angle, and having been photographed by the high-res camera from Lunar Orbiter 2, and it was impressive, right? You can see the peaks in the center of that crater with more detail than anyone had ever seen before, and you can see here off to the side, the Globe has sort of used a quote here, featured a quote. It's almost as though a photographer actually stood inside the crater to take these shots. So folks were pretty impressed. It also made the front page of the New York Times. So they didn't call it the photo of a century, the Boston Globe did. And you see that, though, quoted all the time. So the New York Times, because maybe they were avoiding hyperbole, doesn't get to be the paper that gets quoted on that image. Boston Globe gets it. So here, that image was taken November 23rd, 1966. The way that the camera system worked was it took the two images simultaneously. Both lenses were always used simultaneously, so you would always get the wide angle and narrow angle shot at the same time. So there you see Copernicus crater up here on the ridge, and here you see the close-up image of the interior of Copernicus crater. And if you took a lot of these, especially the wide-angle images, and mosaic them together, you could start to map the moon in Lunar Orbiter imagery. And this is what they did throughout the Lunar Orbiter program. From Lunar Orbiter 1 to 5, they built mosaics of the lunar surface, and this is the way that they started thinking about good landing sites. In addition to the surveyor imagery, these were the images that were used to get a global view of what the different terrains of the moon looked like. And it was orbiters 1 through 3 that were the ones that were there mainly for Apollo landing sites. So they had equatorial orbits. So they orbited around the equator of the moon and were looking for safe landing sites, or the imagery was being used to look for safe landing sites in that equatorial region. That was considered to be the safest spot for landing. By the time Lunar Orbiter 3 was done with its mission, they had accomplished that goal. So Lunar Orbiters 4 and 5 were put into polar orbits and were able to complete that mapping of the moon. And from the scientist's perspective, see some things that were more interesting than the equatorial regions, because nobody had ever gotten a really good look at the poles of the moon. And this mission allowed them to do that. So what do you do with those images once you get them? I mentioned earlier that Tim Much had gone off to spend time at the USGS Astrogeology branch. So the Astrogeology branch had been founded by Eugene Shoemaker, who you may know his name from other space exploits. For example, there was the Shoemaker-Levy comet that crashed into Jupiter back in, what year was that? 94. So, he was a very active scientist in the planetary science community, and he really pushed the USGS to become involved in lunar research. And the fact that the USGS already had a mapping division built into it meant that when it came time for the government to make decisions about NASA funding, and NASA said they wanted their own mapping division, the government said, well, the USGS already does that, go to them. And so Eugene Shoemaker was able to take advantage of that. And he, back in the 1950s, before any of this photography had even been taken yet, had foreseen that this would be a possibility and had written up his own proposal for how to do stratigraphy of the moon, mainly using telescopic photos at that point. So it was a natural fit for him to push USGS towards doing photogeology of the moon. And then you have characters also like Farouk Elbaz, who became the secretary of the Lunar Landing Site Selection Committee within NASA via his position at Belcom, a company that was providing engineering support for the Apollo missions. And Farouk Elbaz eventually became the head or the founder of our Center for Earth and Planetary Studies at the National Air and Space Museum. But at the time of Apollo, he was a pretty young geologist and managed to sort of work his way into a position of quite a bit of authority there at NASA, determining from those photographs, using photogeology techniques, what the landing site should be. And the tools of the photogeologists are pretty simple. They are stereoscopes, a lot like those original stereoscopes that David talked about that were used primarily for entertainment. The USGS had developed methods, and this wasn't unique to them. Army Corps of Engineers had also developed similar methods, and the two had sort of shared their understandings and technologies. But using aerial photography, stereoscopic aerial photography, they would create geologic maps and also extract geologic information from photography using stereographs and sort of sitting very studiously like this over a table, looking through the stereoscope at the images and drawing by hand while looking at the stereoscope. It's a technique that I think probably takes a lot of practice. And so when Thomas Much wrote his textbook, which I introduced you to in the beginning of the talk, he said, well, we almost got stereoscopic views of the moon, but it's not stereoscopic. Instead, what we have is opposite illumination. We have cases here where you have sunrise and sunset images of the same forms. So you can extract some of the same information that you would through stereoscopic viewing and through traditional photogeology. So here he's showing you Sinus Iridum and noting how you can make out different aspects of it with different lighting. And together, if you put the information together, you have a much fuller view than you would get from just one photograph. And here he's talking about the same thing here with another landform. So it essentially took, through Much, through Shoemaker, and through Elbaz, and others like them. I could list off many other names, but these are three of the most central characters, turned the traditional techniques of photogeology of the Earth into a new field of orbital geology that could be applied to the Moon and later to Mars when Mars exploration kicked off. And that tradition continues today. So you've seen so many images of Copernicus by now, but here's Copernicus again, as photographed by the Lunar Reconnaissance Orbiter, a much more recent mission that's orbiting today around the Moon and sending back images. You can see there's quite a lot of more detail there, and this isn't even the highest resolution version of Copernicus imagery from that mission. Take a look at those peaks, those central peaks where you can actually see the grains in the lunar soil, and compare that to the picture of the century returned by Lunar Orbiter 2, right? We have definitely entered into a whole new world, and we now know the Moon in much more detail thanks to these more recent photographic or imaging missions than we ever have before. So that's it. That's my story.
Well, thank you both, David and Matt, for really laying the groundwork for what I'll talk about today, which is we've looked through telescopes, we've looked through robots, now we're going to look through the eyes of the astronauts themselves. And it was 50 years ago, of course, that humans made footprints on the Moon for the first time. And that footprint's still there today, thanks to there not being an atmosphere. And so, of course, if we made footprints on the Moon, we were going to need to take pictures of them. And the person that took this created, obviously, a moment that was significant in terms of achievement, but also it's sort of transitioned now into something that's symbolic and iconic and evidence for all time that we, in fact, did do this thing, this amazing thing. And thanks to the digital technologies of today and the internet and social media and websites that allow you to look through these catalogs of images, it spreads around the world, and so knowledge of our journeys to the Moon can travel quite easily. We don't require newspapers anymore. We can do it via the internet. And so these photographs, more than even the rocks or the stories from the astronauts or movies that we might see on Netflix, have the ability to live on in our shared memory of a time that some of us don't even remember personally, and I'm one of those, certainly. I've wondered what makes an image like this and others that I'm going to show you mean so much to people. And so I'm going to look at this a little bit more from our own perspective, but because of the presence of the astronauts. What makes us feel proud of landing on the Moon? Why do we use them pretty much anywhere you can think of? You can even buy a sweatshirt now that looks like Neil Armstrong's spacesuit. But these appear all over the place. Why have we done that with images that really had a different purpose? As Matt indicated, and certainly as David did as well, images of the Moon from whatever perspective are usually in the service of science, and in this case, the service of geologists in particular. So what was it that brought us to this point of looking at the Moon through the eyes of the astronauts? And I'm going to backtrack just a little bit to before we got to the Moon, and what we were sort of expecting by that time in the late 1960s when Neil Armstrong and Buzz Aldrin stepped on the Moon. Our initial views from astronauts through the cameras and through their eyes were spectacular. These weren't things that we hadn't necessarily seen before, but we hadn't seen them from the perspective of a human holding a camera, something we could all identify with. And so this is an image of our atmosphere, or what's called the air glow layer, during John Glenn's Mercury mission in 1962. And it just kind of gave us reason to want more. It's spectacular. We were able to obviously put ourselves in the shoes or in the spacesuits of the astronauts to think about what they were seeing, as opposed to trying to imagine what it might be like to be on a spacecraft that's just robotically controlled. So 3 years later, we moved on to something that's even more spectacular. We got to see actual human beings in space. Project Gemini, this is the first spacewalk by an American, Ed White, in July of 1965. And we can see exactly what it looks like to be in space, to live and potentially work there. It's put on TV, it's on magazine covers and newspapers. These are things that are becoming sort of publicly consumed in a really broad way. And we can, of course, because we can see a person there, it's an identifiable shape, we can imagine ourselves being that person. we know that they are in space. It's not just from the backside of the camera anymore. We can see the people actually carrying out activities in space. But these were, if nothing else, proof that we were actually doing this, that maybe taxpayer dollars had actually gone to something useful. But it provided what kind of is the reverse of what I'll go on to talk about. It's also the beginnings of something called the overview effect, which is a phrase that kind of comes up much later than the Apollo program or the Gemini program even, but it's the way of seeing Earth as opposed to seeing the moon that sort of reshapes our vision of what it is to go into space. It's looking back and seeing the Earth as fragile, not looking at the moon and imagining what it might be like to go there. But we do go there. We go there on Apollo 8, as Matt mentioned. We have the Earthrise image that's captured in late 1968 by the Apollo 8 astronauts. It's a game changer. It's seen on television first during the crew's famous Christmas Eve broadcast, but that was black and white. It was kind of fuzzy, and it's a long ways from the moon, so you're not necessarily going to get the high quality that you would out of a photograph. And so Frank Borman and Jim Lovell and Bill Anders were seeing this site, and I think this photograph obviously really expresses exactly the words that they used, that Bill Anders in particular used, was, wow, look at that view. And so it is a spectacular, sublime view that they're seeing, but it's also giving some real life words to the things that had already been seen by those robotic vehicles just a few years before. And most of you are probably wondering why this image is tilted the way it is in portrait view. And that's because this is the way the photographer actually intended it to be seen. And we talked a little bit about this before we started today. There's no up or down in space. So it's all about how you perceive your orientation to other objects. We're familiar with landscape views because we stand on the Earth. But Bill Anders wasn't standing on the moon, and neither were any of the astronauts in the spacecraft. But the way that Bill Anders intended people to see the view of Earth was as the spacecraft was going around the equator. They orbited at the equator as well. And when he looked out the window, this is the view that he saw. And so that's his interpretation of the view. Frank Borman did see it as a landscape. That's the way he was pointed when he took his picture. And so if you saw the black and white version that Frank Borman took, you would see it in landscape. But for the most part, we usually see it in landscape, and that's because that's what we're familiar with. So based on our own human experience, we have expectations for images of space flight. It's the ones, they don't always obviously fit our expectations though. We've shaped that by our personal experience, but also by the experience of other explorers, people who went around on the Earth and saw similar sights as what the astronauts would see. And so my argument is basically that there's a set of expectations going into Apollo, not only in terms of science, but also in terms of just the general exploration of the moon that has already created a set of understandings of what we'll see once we finally get there. And that's based on, as I said, exploration of Earth. And so there are these other exploration efforts throughout our history that sort of set up this visual rhetoric that you then see carried out by the Apollo astronauts as well. You've got certain themes that arise across all of these efforts. You see the horizon. And so when geologists are carrying out their expeditions in the American West, they want to show these long distance views of the horizon. And likewise, during exploration of the Antarctic, photographers are out there taking these same kinds of views of the distance. And of course, during the Apollo missions, we're seeing Earth in the distance. And it leads you to wonder, begs the questions. You as a viewer you're curious about what the foreground holds and what just might be over that horizon. Another theme is sort of the theme of accomplishment. There are people in these images. That's what makes them distinctly unique from those robotic images. You could actually put a person in these views. And so you have views when people have come across something that they've never seen before that's particularly exciting. In the case of the expeditions to the Antarctic up there on the upper right, they're excited that they might be rescued. This is during the Shackleton's trip, and that was one of the boats kind of going off to rescue, to go off for rescue. And so these guys are not necessarily excited to see the boat. They're seeing the boat off and giving a lot of, obviously, signals of hope. But then for the Apollo missions, we have countless images of celebration, and sometimes that takes on a particularly nationalistic tone, but people around the world are celebrating these because they're seeing people in these locations that we would never have seen otherwise, or we would never have seen through their eyes without these types of images. And so we can celebrate along with them. But it's also important to understand how we got there. The moon is an unfamiliar place, just as some locations in the American West or Antarctica itself are sometimes still unfamiliar to many of us if we haven't traveled there ourselves. So you have to have some sense of how people got there, no matter how foreign or familiar those methods of transportation might be. And so we see boats, we see large ships in the background of images. And in the case, of course, of Apollo, we see the lunar module or we see the lunar rover. We see the methods of transportation that are important to connecting the human to the location. But again, the human becomes a really important part of understanding the landscape. You're not just seeing from the robotic perspective of an orbiter or through the eyes of that elevated camera on a surveyor lander what it looks like around that particular location. You can get a sense of the location even better if you can see a person up next to some of those features. And so you've got someone standing on top of a glacier, or you've got someone standing next to a large ice formation in the Antarctic, or you have an astronaut standing next to a gigantic boulder. That really gives a sense of just what these kinds of landscapes offered us in terms of research. But it also gives us a hint, especially in this case, of the kinds of things we might begin to see when we go to another location, if humans are to go. And this is a question, of course, we tackle at the museum all the time, because young people in particular want to know what comes next. It's not just about what's happening today, it's about what comes next. And with promises of going back to the moon or to Mars, we can expect more of this. It will be similar, and you can see that already in some of the images that have come from our robotic explorers on Mars. We're looking to see some of these similar themes play out in each of those. So we have our robotic friends who have traveled around on Mars, and we even see their own portraits taken from cameras that can be elevated from quite a distance up. But what are the things that we used to take these photographs on the moon? So you need a really great camera. And the Apollo astronauts had a number of cameras. They did create stereoscopic views using a Kodak camera that actually Eugene Shoemaker, I believe, was involved in creating. But Kodak created that camera to take those stereoscopic views. But for the images that we knew we were expecting, that NASA expected, but also that scientists would expect, and from this point of view, you needed something that was easy to operate, something that could be familiar and would be very flexible and easily managed inside a massive spacesuit that would have to be worn to protect the astronauts. So they use something that's basically off the shelf but modified for astronauts to some degree, and they select a Hasselblad camera, which is what you see here. This is the Hasselblad camera used by, not on the surface of the moon, but it was used by Michael Collins and the astronauts in the command module during the Apollo 11 mission. And you can see there are some accommodations made for the fact that astronauts have to wear spacesuits. It has a little tab down here that's been added to the lens to be able to change the position. It's got some Velcro in case they need to stick it up against the wall. And there's some other slight modifications and some, of course, little pro tips on little settings and things that they could do. The astronauts trained considerably for these missions, but they did have to have lots of backup mechanisms just in case they forgot exactly what they were supposed to do. So the modifications that you can't see include things like films. David mentioned films and having special emulsions and things made. So, of course, NASA reached out to companies that would know how to do those things and do them well. So they wanted to fit as many frames in there as they could, and so these magazines traditionally would have had about 70 frames on a roll of film. These ones were able to accommodate 200. And so by using a very thin film, they were able to obviously put more frames on there. Kodak was heavily involved in that process. They also modified the shutter so that there were, it had special lubricants on it that wouldn't be affected by the different kinds of atmospheres the astronauts would be encountering inside the spacecraft and later outside the spacecraft. And they wanted to remove as much weight or glass. Glass is a pretty bad thing to have break in space. It would get all over the place and create quite a bit of damage. So there's no viewfinder. The viewfinder would have been very heavy, but it also contained more glass. There's no mirror inside this camera. So they're really trying to streamline exactly what they're going to use in space. And typically these don't come back. These are the ones that are inside the command modules, so they're a lot more, it's easier to bring them back. The ones that go to the moon that you often see in the photographs are painted silver or made with silver metals. Those most often stayed on the moon, though some of them did return. So what does return from the surface of the moon, especially during Apollo 11, are lots of magazines. Here we have the magazines that are in the museum's collection, and I think one of these is on display right now over in the museum. These are the magazines from Apollo 11 that returned, magazines R and S. And you can actually go online and find out what actually just came off of those magazines, what they were particularly used for, what photographs. But 142, over the course of the Apollo program, 142 of these Hasselblad magazines returned, which accounts for just over 18,000 photographic frames. The highest number being accumulated during the Apollo 17 mission, the last mission to the moon, and the least, just 5 magazines coming from the Apollo 13 mission, which I think is probably not a huge surprise if you know the Apollo 13 story. And so they come with these pre-printed labels, really giving the astronauts all the instructions they could possibly need when they're using this magazine and how to prepare the cameras. It's a great little cheat sheet for them to be able to do this, and they have all these imprinted guide in their mission manuals as well. They're all of the documentation that they're carrying with them. And so they bring back images, though, of things that we had never seen before. We see people on the moon. We see, of course, in this image, something that has really transcended all different places in all different applications. Some of the things I like to talk about when I see this image are the ways it becomes what we think of today as viral, because this image in particular has had quite a life of its own after it was returned from the moon in 1969. It becomes inspiration for artists. Andy Warhol has a very famous take on this photograph. But this is also then becomes a bit of fodder for other types of media outlets who want to consider themselves Apollo-like or astronaut-like or revolutionary, something that kind of speeds up something to a level that we've never seen before. And in particular, the TV channel MTV took this image on, and many of the Apollo images and later shuttle imagery as a sort of way to express their own sea change, what role they play in culture is sort of shaped the same way as the Apollo images sort of changed the way we look at something. And so up until recent years even, this image was the inspiration for their statuette that they would give away for one of their awards. And one of them even flew, and kind of completing the circle of this story, one of those statuettes eventually went to space, to the space station Mir in 1996. And so these are some of the visual cues that my generation in particular, and I think generations that follow mine, are going to have for understanding Apollo images and understanding what it meant to take pictures on the moon, is that these things, there are ways that they can connect to these moments and to these images that they're not necessarily expecting. But I want to look at one image in particular in some detail. And David brought up the idea of images as evidence. And this is one that I like to use particularly because it is a very close view. It is captured with a Hasselblad camera. It's not a stereoscopic image. It is one that you can look at and understand what is the utility of putting a person on the surface of the moon, and what are the things that we could learn from the image itself. And so one of the things that didn't exist, as Matt brought up, that didn't exist for those lunar orbiter images was some way for geologists to be able to measure distance. And so that's one major feature of Apollo images, is the addition to the magazines of a Rousseau plate, which allows them to then mark out exactly what are these distances. So photogrammetry becomes something that's much easier with these Apollo images, these astronaut images. They become incredibly useful to understanding the surface. You can also interpret from these images a great deal of the scientific information that isn't expressed necessarily in the samples that are returned from the mission. So you can understand the actual texture of the moon and the way in which the lunar regolith is sort of how it actually adheres to itself or creates this, or it's interacted with. So the story of this particular image, it's an image as part of a sequence that Buzz Aldrin took while he had the Hasselblad camera in his possession. Armstrong was actually the primary photographer for the mission. One of the reasons that you don't see images of him is he was mostly the photographer for the mission. But Aldrin had the camera, and I happened to ask him about this recently, about this particular image, because I have used it so many times. And what he explained to me is that he took a series of images because he wanted to get a very clean, pristine view of what his boot print was doing on the lunar surface, because he had noticed this and he wanted to actually show it in a very clean way. And there's another image I'll show you in a second that shows this is part of a sequence. So what you could tell from this is just what the consistency of the material is. You can also tell the sun angle. So he's pointed, the sun is over his shoulder. I noticed in one of the books outside that this image was actually flipped upside down, which would be quite impossible to take the image from that view, because you wouldn't be able to move your boot, you wouldn't be able to pull your leg out in that direction. It just doesn't work. So his description of how this image came about is that to get this pristine view, he had to find a spot that had been untouched, and then he had to actually put his foot down and lean backwards in order to not drag his boot out of that spot. And so that's why there is this great big shadow at the bottom, because the indentation of his boot was quite a bit greater at the backside where his heel was as he kind of pushed himself out of that spot. So it tells, we have these multiple layers of information to be able to understand exactly how these images came about and what they can tell us and what the astronauts are really trying to tell us during their experiences on the moon. And here's one of those early versions of what he was trying to do. He's showing that, obviously he's creating these boot prints. And there's lots of symbolism that one could read into any of these as well. But you can also tell there's quite a big difference between seeing an image that's color corrected and not color corrected. So this one is, they're also, I should say, using black and white film as well, which gives even a greater contrast. So those are even incredibly more valuable. This might be more valuable to scientists than some of those color images. But this isn't the only way that people remember seeing the moon. And so seeing the moon comes in a couple different ways. And one of the ways that is often related and often spoke of more than the photographs is the live television broadcast. And this is the camera that was created this is a camera, a version of the camera created to capture those first views of the moon and send them back to Earth. And so this is obviously a huge part of sort of our narrative of the late 1960s, and something that came up in, obviously for us over the summer, in relating the story of the Apollo 11 landing. But it's also not easy to replicate these. You can broadcast, but reproducing them and viewing them again and again. And I think this is something that's often lost on a lot of our younger visitors to the museum, is in 1969, it wasn't possible to go to YouTube and just replay the whole thing over again. We didn't have those kinds of mechanisms you didn't even have VCRs back then to be able to replay that recording. And so to see it once was one thing, and it imprints on your memory maybe, but it's not something that you can repetitively encounter. And so those photographs become really the best way to kind of re-encounter those moments over and over. Here's the camera as it was on the spacecraft. They had to stow it this way in order to make it all work. It then was flipped down through a lanyard system by Armstrong as he got down the ladder. And so then NASA had to kind of reverse engineer all that back on Earth. The signal came back to Earth through a very long route through satellites in Australia and receiving stations. And so it's kind of a long winding road to the television in your home. And NASA then, of course, had to flip that image back over too because the camera's pointed well, it's kind of upside down, obviously. But about 500 million people watched that live broadcast, which is about 7% of the world's population at the time. And that's a high percentage of the U.S. viewers were tuned in, of course. Of 125 million viewers, there's about 53, of 125 million people in the U.S., that there's about 53 million households that are watching this. So it's viewed, obviously, quite widely. And what do they see? They see this image. It's fairly fuzzy. There's lots of, as Matt was explaining with some of the television, the way that the images are sent from lunar orbiter, you've got the same kinds of issues, same kind of technique. That you've got the camera, the television camera sending the signal, but you've got a long ways to travel. You've got issues of routing that signal back to Earth and back to someone's television. And so the quality of the signal is fairly low. And there have been with the lunar orbiter images, been lots of efforts to redigitize some of this material. There's been searches over the years for the best quality tapes of that particular moment and how could we improve upon how we see the first steps. And so there's lots of techniques that have been tried. And it's gotten significantly better from what people probably saw on television in July of 1969. But how we see spaceflight today, since Apollo, is different. And even in my childhood, during the space shuttle era, you could simply turn on CNN and watch a launch. But that doesn't really happen today. Did anyone even know there was a landing today in Kazakhstan of some astronauts? So if you follow the space program, you might know that it happened. But otherwise, it's kind of invisible to most of us. But it's certainly not stopped or slowed down. It's only accelerated the way in which astronauts use photography to carry out their mission. There are lots of scientific photographic studies happening from the space station today. And you can actually kind of compile some of those themes I showed earlier into a single image. So here you can see the spacecraft, and sometimes you might see people in this image. You can see the Earth's horizon. You can see, you can imagine how people got there. And so a lot of these themes are kind of, layered on each other in a way that we haven't seen before. And you can share these much easier. Astronauts are sharing these images on social media, and so they're circulating in a much more free way than they would have previously. But we can take these Apollo images now that they're available online and share them and circulate them and really turn them into something much different, I think, than they were originally intended. I mentioned earlier that there were about 18,000 images taken by Apollo astronauts. There are tens of thousands of images coming down from the space station each week. It's so great that there are not enough people to catalog them on the ground. They go into servers in the Southwest and then into Houston, and there are just not nearly enough people to catalog each individual photograph. And so it's exponentially higher, but we still are seeing the same kinds of things. And we'll, of course, be able to continue as long as the space station is orbiting, continue to study Earth from a visual perspective, from the astronaut perspective, with some of the views that they're looking for. And scientists can go and request new photography of particular locations. Geologists can ask for that and get these kinds of returns where you have really high detail. You can study and of course, this is all available over the course of time. You can actually go into databases and look for images of exact geographic locations and view them over time. But you can imagine that this view is obviously quite a bit different than we understand this image in a much different way than we would understand it if it's taken by a robot. Google Earth does a similar, obviously we could view something similarly, but that's not taken by an astronaut. So it makes something like this feel much different, which is home. You can see these things down to almost the street level. And this image from just a few years ago, which happened just to be the best image I could get of the Washington, D.C. area online a few days ago, shows that we're seeing ourselves in a new way. We're able to look at almost a street level view of what it is we know every day. And so instead of looking at the moon, the space program in particular, in relation to the astronauts, is looking home. We're looking, 6 people are orbiting right now at about 250 miles up. And I think there is something certainly that changes our perspective when we know that there is an actual person behind the camera. And that changes certainly how we view and have viewed the moon, but also ourselves as we still stand on planet Earth. Thank you.